Okay. Nice. Okay. Thank you. Thanks for the nice introduction. And I'm very happy to see there are so many audiences. And actually, I know many of you in many different conferences. So I'm happy to discuss with you. So you can interrupt me anytime to ask questions. And hi everyone, I'm Zhenhuan Liu from Tsinghua University. And so my research is mainly about quantum learning, like entanglement detection, like random benchmarking, classical shadow, something like that. And my published papers also include like quantum algorithms, quantum foundations, quantum many-body physics, and quantum error mitigation. So and about today's talk, my plan is to first introduce a posted paper, which is predicting arbitrary state properties from single Hamiltonian Quench Dynamics. Oh, by the way, can you see my mouse?
Yep. Yeah.
Okay. Nice. And this work is about analog quantum simulation and classical shadow. And you can screen this. You can use this code to get this paper. And after this, I will share some of my ongoing projects with you, which is about learning with purification, environment learning, and entanglement detection with you. I hope I can have some nice discussions with you. And okay, so let's get started. The first work is a joint work with Zhenhuan Liu. He was an undergraduate student in Tsinghua University, and he's now a PhD student in UC Berkeley. And Hongye Hu, he's a postdoc in the Harvard University. Okay, so let's start from background. Basically, our motivation is from the analog quantum simulation. So we know that analog quantum simulation aims to solve quantum problems using quantum computer, and which is actually the original motivation for the quantum computation. And until now, the analog quantum simulation has become an important routine for many-body physics, quantum phase estimation, superconductivity, and basically many researchers now believe that the analog quantum simulation can demonstrate some practical advantage using the current quantum devices. And actually, the analog quantum simulation is very similar with wind hole experiment. So let's imagine the simplest case. For example, we want to simulate the quantum many-body system, and you have So our task is that we want to ask the properties of a quantum system after the evolution of Hamiltonian, like e to the minus iht, and at the same time you have a controllable quantum system in your hand. So what you should do? So the most intuitive way is that you can use your quantum platform to you can evolve your quantum system using this Hamiltonian, and after this evolution, you measure the target properties. So basically, many analog quantum simulators are specially designed quantum simulators to solve some special problems. And basically the Hamiltonian form of this analog quantum simulators are restricted, and maybe sometimes they are restricted by some symmetries or global pulses. So the most important thing is that most analog quantum simulators has no universal gate set. But maybe you will feel that it is okay for analog quantum simulators because the target of analog quantum simulator is just to simulate some specific, it's just to solve some specific quantum problems. So maybe I don't need the universal gate set. However, this will cause a very big difficulties in the quantum measurement. So basically, extracting some classical information from a quantum system is the final step of all the quantum information processing tasks. And for example, maybe at the end of some analog quantum simulations, we want to estimate the expectation value of some observable O. What we should do to estimate this observable? I think the easiest way is that you can perform some unitary on the target unknown quantum state rho to rotate the state rho into the eigenbasis of the observable O, and then you perform some computational basis measurement on this evolved quantum state. Then you can classically compute the expectation value of this observable. However, you can see that if you do this, if you want to do this, you need to perform some fixed unitary which is determined by this observable. However, as we said before, the analog quantum simulators had no universal gate set. So basically, it is very hard for the analog quantum simulators to perform some fixed unitary determined by this observable. Because of these difficulties, many analog quantum simulators are restricted by some very limited properties like the particle number correlation function for the quantum gas microscope and some identical polystrings for the readable atoms with global pulses. And this is basically what we want to solve in this work. Okay. You can ask me question anytime. And no questions, I will just continue. So basically, after the proposition of the classical shadow protocol, many researchers think that maybe classical shadow is a way to solve the difficulties in analog quantum simulation. The reason is that if you are familiar with classical shadow, you know that the classical shadow does not require any fixed unitary evolution. So basically, classical shadow uses a random unitary evolution and a computational basis measurement to they can use this data to extract arbitrary properties from this unknown quantum state. So basically, classical shadow does not require any fixed unitary evolution. So it seems that the classical shadow is more suitable for the analog quantum simulators. However, the original classical shadow protocol, they require the random unitary evolution to be either the random Clifford gates or the random Pauli gates, and these gates are still challenging for the quantum analog simulations. So after the proposition of classical shadow, there are many researchers pay some efforts in modifying the original classical shadow protocol and make it more applicable in the analog quantum simulations. For example, in this work, this is Hongye's work. They propose that maybe we can use random Hamiltonian evolution to achieve the classical shadow. So basically, this means that in each experiment round, you can randomly choose a Hamiltonian and use this random Hamiltonian evolution to replace the random unitary evolution in the original classical shadow. Okay, so basically this protocol is kind of ideal but not very practical because a very important assumption of the classical shadow is that you need to have the information of this random unitary in each experiment. So if you want to use random Hamiltonian evolution to achieve to realize the classical shadow, you need to collaborate this Hamiltonian in each experiment. So it is extremely expensive. And there are some other work and this is the work from your group, and basically this work they try to limit the performance of classical shadow. So basically, the original classical shadow can estimate arbitrary properties, but we found that if we can restrict the properties of the achievable properties of classical shadow, for example, maybe we only target at measuring some correlation functions, then we can use some easy evolution to realize the classical shadow. Like in your work, you use the fermionic quantum, the intrinsic fermionic Hamiltonian evolution to realize the the classical shadow, but you can only estimate the correlation function properties like the correlation functions. And another work that I think is very interesting is this one, which is a PRX paper written by some MIT researchers. So their main idea is that so our target is trying to realize some random evolutions. So their way in their methods in realizing the random evolution is using some ancillary qubits. So basically, they propose that we can evolve the target state and some ancillary qubits using some joint evolutions. And after this joint evolution, you perform some measurements on this ancillary qubits. And because these measurement results of these ancillary qubits are random, so if you get some memory results like I, then the target quantum state will evolve by some random cross operations or random cross operators. So although this is not a random unitary evolution, but you can also use this random cross operator evolutions to realize the classical shadow. So you can see this is very good because we don't need to use many different kind of evolution. We only need to use a single evolution and some ancillary mode to to realize random evolutions.
Can I ask a question, or like more like a meta question? It's not really, but I mean, on the highest level, I mean, there's like properties of states to be learned, and then you do this by appending some as simple as possible, like random evolution, to then like apply some classical shadow technique and like undo some of the quantum evolution. And people have looked at many incarnations of that. You said it yourself. I mean, for example, using quenches in many-body settings. We looked also at logarithmically deep circuits and so on. Now you include measurements to think of like simpler quantum protocols to get the shadow done.
Yeah.
Like one argument that's sometimes used as a devil's advocate argument against classical shadows is that it's a cool and compelling scheme, no doubt. But this idea of like predicting many properties at once from pre-measurements, this is like something that's not so important after all. Like theorists get very excited about this, but when you talk to experimentalists, they say, yeah, cool, but we just want one specific quantity and we just want to read it out. I mean, there's no need to learn all properties or many. We just want to learn what we want to learn. Yeah. So
yeah, of course. So actually, I really appreciate your work.
My question is like, to what extent, but this we can discuss later, one can tailor like the specific random quenches, measurements, and so on that you do to the family of properties that you're really concretely interested in.
Yeah, of course. I think this is a very interesting question. I actually, after I read the original paper of classical shadow, this is a problem I want to ask. Like for example, I know that all the observables, all the properties I want to estimate is in some like subspace of the observable space. Can we use some random unitary with some simpler forms to achieve this to estimate all these properties? Yeah, I think this is a very good question. Maybe we can discuss later. Okay, is there any other questions? No. Okay, so basically this work is using some ancillary qubits to introduce the random unitary evolution, and I think this is very interesting work because at the same time I came up with the same idea, but after I finished all the derivations, I saw this paper on the archive. So this is a very sad story. Okay. Now you can see that although we have many progress in this direction, there all the existing protocols requires either that you need to limit your properties, limit the performance of the classical shadow, or you need to double the system size. Okay, so basically this protocol requires you to double the system size. And if you want to double system size, you know that the dimension of the whole system is the square of the original system. So this will introduce many causes in the classical simulation or in the quantum control. So our question is that can we like further reduce the cost in the classical shadow in analog quantum simulations? Okay, so now I want to introduce our protocol. And basically, we found that I think this is quite interesting because after proposing this Hamiltonian shadow protocol, we found that actually this it is actually very easy to perform the classical shadow in analog simulations. And our protocol is very simple. Basically, what you need to do is just to evolve the. Okay, so now rho is the target state, a target unknown state, maybe produced by your analog simulators. And what you need to do is just to perform a Hamiltonian evolution in each time with a fixed Hamiltonian and a random time. And after that, you perform some projective, some computational basis measurement to get some measurement results. And after repeating this process for many times, you get some data about the measurement results and the evolution time of each experiment, and the Hamiltonian you use in this whole experiment. Then we proved that you can use this data to classically calculate arbitrary properties of the target quantum state rho. Okay, so let's summarize some advantage of our protocol. So basically, our protocol only requires a single Hamiltonian, and we don't require any ancillary systems. And at the same time, our protocol can predict arbitrary state properties. So basically, this means that this whole setting is tomography complete. And what is even more better is that our protocol, the sample complexity of our protocol, as I will discuss later, we found that the sample complexity is actually comparable or very similar with the original class of shadow based on global Clifford gaze. And at the same time, our assumptions of the Hamiltonian is minimal. So basically, if you have a analog quantum simulator, if you are an experimenter and you have an analog quantum simulator, and the Hamiltonian of your analog quantum simulator is determined by your by the physical properties of your system, and you cannot easily change the Hamiltonian. You can directly apply your system, directly apply our Hamiltonian shadow protocol in your system, and with a very high probability, our protocol can be applied in your system because our assumptions of this Hamiltonian is minimal.
Can I ask a question? I mean, this is like super. Of course. And like, what's the price to pay? Like in this. On log depth circuit. I mean, there's some authors are actually also in the call. We saw that you can get away with log depth circuits instead of full Clifford circuits. But at the expense of like having a more tedious like tensor network-based classical reconstruction. But comparable. But is there a kind of an overhead in classical post-processing that you get by using these simpler Hamiltonians compared to like random Clifford circuits as in the original scheme?
Yeah, very, very nice question. And this is what I want to say next. So I already tell you some advantage of our protocol, but I need to tell you that there's some disadvantage. There are two main disadvantages. The first disadvantage is the evolution time. So basically, the random evolution time, you can in each experiment you can randomly choose the random evolution time in some like time window. And with the first disadvantage is that the length of this time window might be exponential in system size. The second thing is that the post-processing is very expensive because basically our post-processing, classical post-processing requires you to perform some spectral decomposition on the Hamiltonian. So the classical post-processing is also exponential in system size. But we want to emphasize, what we want to emphasize here is that I think this price is necessary because in this work, our target is to design some like very general protocols which can be applied to the analog simulators with arbitrary form of the Hamiltonian. So because we don't want to have many assumptions on the Hamiltonian, so this price is might be necessary. So I really appreciate your work about the classical shadow in the fermionic quantum states system. So I think your work can be regarded as a special case of our protocol. So this shows your work shows that if the Hamiltonian has some special forms, this all this price may be reduced if we have some assumptions on the Hamiltonian.
So maybe I also have a question, just to be clear. You say that you need to evolve with the Hamiltonian for exponentially large times and to diagonalize the Hamiltonian. Or did I get this wrong? Did you say that you need to diagonalize the Hamiltonian for the post-processing, or this I got wrong? Sorry.
Yeah, you are right. We need to diagonalize the Hamiltonian. Okay. I will tell you the reason.
Okay.
And I will give you some intuitions of why the evolution time should be very long.
I can imagine later. A lot. Yeah.
Okay.
Thank you.
Thank you for your question. Is there any other questions? Okay. I think maybe this is the process of this protocol is very easy. I think the most important thing is the most interesting thing is why this protocol is why such a very simple protocol is tomography complete. And let's say some intuitions of this protocol, some geometric intuitions. I like intuitions. Okay, so let's take a very simplest case. For example, this is the Bloch sphere of a single qubit state, and in this Bloch sphere, the quantum state we want to the target quantum state is some vector. It's a vector, and our target is to know the position of this vector. But what we have is that we know this state is evolving under some known Hamiltonian. And geometrically speaking, this means that in this Bloch sphere, the vector of the state is rotating around a known x with a known angular velocity. because the axis and the angular velocity are all determined by this Hamiltonian. So we know this state, the vector of this state is rotating around a known axis and with some known angular velocity. And at the same time, because we perform the computational basis measurement at the end of this at the end of each experiment, so actually we can know the we have the information of the z position of these rotating vectors in many different times. Okay, so now this problem now completely becomes a geometric question. So if we know the state is rotating around a known axis with a known angular velocity, and we know its z positions in many different times, can we decide the position of this state vector at the initial time? If you take some seconds, you will see that this is possible. You can use all this information to decide the position of this row of the vector of row. And I also want to ask you a question. So can you say that maybe in which cases this protocol fails? In which cases this
Hamiltonian, this will fail, no?
Can you say it again?
For degenerate Hamiltonians, this will not work.
Yeah, this is the first thing. Can you tell another case from this picture? Okay, I will just tell you the answer. So basically, you can see that if it is easy to say that if the Hamiltonian, if the direction of this Hamiltonian is parallel with the z direction, in this case, the rotating plane will be vertical to this z axis. Then in this case, you will find that the z position of rho is not change, does not change over time. So in this case, you cannot tell you cannot decide the initial position of rho. But if there's any questions, you can ask me, because this page is really important. So if you are not very interested in the quantum learning things I will discuss in this page in this talk, after understanding this page, I think you can just leave this Zoom.
Okay. I actually both. I'm both interested in the learning part, and I have a question.
Okay.
I mean, is there an issue of, well, maybe that's a stupid question, but I mean, is there an issue that the Hamiltonian needs to be known very accurately, or in other words, how accurately do you need to know the Hamiltonian? I'm sure to exponential precision, right?
Yeah, this is very important. So in that work, we assume the Hamiltonian is completely known. We did not analyze the robustness of our protocol. We just performed some experiments to test the robustness.
But I think this is to show that if you like, I mean, that would be a nice add-on, like to show that if you like operator norm close to the original Hamiltonian or so in some suitable sense, then you could still do it. Never mind. I made my point.
Okay. That's a very nice comment. Okay, thank you. Okay, so basically you can see that from this picture, you can see that in addition to some very special case where the direction of this Hamiltonian is parallel to this z direction. In addition to this, if you can if you random select a Hermitian matrix and use it to perform our Hamiltonian shadow protocol, it with a very high probability it works. So this is the reason that why our protocol has a very small assumption for the Hamiltonian. But at the same time, you can also understand from this picture about why the evolution time should be long, because we want the state to rotate around this Hamiltonian with a very random angles, So we need if the evolution time is very small, so this means that the state rho is only move for a very small distance. In this case, this protocol is also tomography complete, but maybe you will pay some price in the sample complexity. Okay, I think maybe my speed is kind of very fast. So if you have any time, you have any questions, you can interrupt me.
No,
okay.
It's okay.
And because I think maybe most of you are are experts in the quantum learning, so I think it is also very good for me to introduce some mathematics, some key mathematics to you, because I think they are really intriguing. So if you are familiar with the original classical shadow, you know that the central thing of classical shadow is the classical shadow map, and the original classical shadow paper, they use the random unitary tool design tool design calculations to determine the shadow map, and we found that our Hamiltonian shadow also requires to calculate the shadow map, and well, the main observation of this paper is that we found that if you perform a spectral decomposition of this evolution unitary e to the minus iht, you will get like vh lambda t vh dagger, and here vh and vh dagger are unitary operators that is not is independent with the evolution time t. However, at the same time, the lambda t, this lambda t matrix is a diagonal unitary. Is a diagonal unitary whose elements is determined by the evolution time t and the eigenvalues of this Hamiltonian and the eigenvalues of Hamiltonian. So if you can, if we assume there's no degeneracy in the Hamiltonian and the evolution time t can be randomly selected, you will see that the lambda t, this matrix, lambda t matrix will approach a random diagonal unitary, So actually, the most initial motivation for me to propose this Hamiltonian shadow protocol is that one day last year, I saw a paper, and I found that for random diagonal unitary, there are also properties like hard measure and random designs, and you can also calculate the twirling over the random diagonal unitary. And at that time, I'm very excited because I think maybe we can use the random diagonal unitary to propose a new quantum classical shadow protocol. And then I think how can we realize the random diagonal unitary? And one day I found that the random diagonal unitary naturally exists in the quantum quench evolution operators. And so in this work we use the random diagonal unitary tool design properties to calculate the Hamiltonian shadow map for our protocol. And I remember that your group recently had a paper about how to design the randomized benchmarking protocols for analog quantum simulation. Actually, after I finish this work, I also thinking about how to propose the randomized benchmarking for analog quantum simulation. And my initial thought is also based on this random diagonal unitaries. But I failed. But I'm very happy to see that you succeed in proposing that protocols.
So can you repeat that again? So it's not the e to the minus iht, which is a diagonal unitary, but the vh. Is it?
No, I'm not saying that e to the minus iht is diagonal unitary. I mean that after the spectral decomposition, lambda t is a diagonal unitary.
I see. Okay.
And if t is random and the eigenvalues of Hamiltonian are different, then the lambda t will become a random diagonal unitary. And the random diagonal unitary also has like random diagonal unitary t design, and we can use the t design to calculate the twirling of it.
Right.
So you take a random, a hard random v or a two design v, and you take a
no. V is a fixed thing.
Sorry?
No. V is fixed because h is fixed.
And then lambda is like each diagonal entry is Gaussian or something like this. Or the phase. The phase is like
Gaussian,
random on the unit interval.
Actually, it's not Gaussian, but very similar. So basically, all the elements of lambda t is like e to the minus I theta. E to the minus I theta.
It's random from the 0 to 2 pi interval.
Yeah. Uniformly random.
Okay.
That's pretty interesting. Like, but so okay, maybe I can ask in the round. Maybe you know, or maybe some of the other attendees know. Are IQP circles conjugated by random Hadamards?
Yeah.
Also two designs?
Yeah, that is a very good question. So basically, in our work, we also analyze the performance of so basically, if I know what you mean. So if you mean that if you set the VH to be the tensor product of Hadamard gate, then this will become an IQP circuit. Actually, we also analyze the performance of that protocol when setting VH to the product tensor product of Hadamard gate. the conclusion is that that is not tomography complete.
Okay.
That protocol is not tomography complete. But the good thing is that the good thing is that you can estimate all the off diagonal terms of rho, but at the same time you cannot estimate all the diagonal terms of rho. The reason is just because the VH has a very special form. So if you are interested in the thing, you can read the original paper. I read that in the appendix.
Okay, thanks.
Thank you.
Can I also ask a question? But you are the captain. I mean, if you ask too many questions, then if that's annoying, then you stop us.
Oh no. That's fine.
Okay. So that's super interesting. I mean, as an idea, but like you also mentioned our work on analog randomized benchmarking. I mean, that looks like a small step, but it was actually quite a fight to get this paper out. It took like years, and it was actually quite difficult. It doesn't look like it, but it was pretty intense. Anyway, it has many nice features, but it has one major flaw, which I can say. I mean, which is that the different particle numbers are a bit separate, and if you have noise models that let the different particle numbers talk to each other, then it's getting a bit funny. So how is it in your setting? I mean, it doesn't seem that the particle numbers matter so much. So would this be applicable also to a setting where you have a noise model where the particle numbers get scrambled?
I'm not quite sure what do you mean, because now I'm just want to estimate the property of basically this work is also is only about estimate the property of a state. So I did not consider the noise.
No, sure, but you will still, well, never mind. We can also discuss this later. But I mean, in your circuit, you will still have a noise. And then if you have a tiny element of the particle numbers talking to each other, then you might have a very difficult time learning the state properties.
Yeah. I think maybe I understand your question. So basically, the difficulties in for our protocol to handle the noise is that there will be a matrix VH. So basically, VH is a very complicated unitary, which is determined by the eigenstates of H. So even if the noise in the circuit is very uniform, then the VH will make the things very complicated. So
to connect to the question I had before, like if you have like your diagonal being random, IID random, like each spectral value being random, is this? I mean, this should be really hard to actually implement physically, right?
What do you mean?
I mean, you would like to get such a Hamiltonian that generates such a thing. You would need a Hamiltonian where all energies are IID random, all energy values.
Actually, I know what you mean, but actually the thing is very good. So basically, we found that if the Hamiltonian has no degeneracy, then it's okay for our protocol. So
that's sort of sufficient for okay.
Yeah. Because you can increase the time, increase the length of the time, and so when because you know that the phase has some periodicity in like 2 pi periodicity. So if you can increase the value of the time, if you can increase the value of t, and if like 2 different eigenenergies of H is different, then the time will make these 2 phases independent.
Okay.
Okay. Is there any other questions?
Yeah, maybe I have a question about this condition of the eigenvalues. Is it just enough that they're all different, or do you need things like that they're rationally independent, things like this, such that the time evolution does not close, you know?
Yeah. Your question is, I think, is similar with the last question. So basically, the conclusion is that no degeneracy is enough. So the only requirements for the eigenenergies of Hamiltonian is no degeneracy. Even if I know what you mean. Even if for example, some eigenenergy is like exactly the twice of some other eigenenergy, this is fine for our protocol. Because
still gives tomographic completeness.
Yes, it's still tomography complete. Yeah.
Thanks.
But then my original intuition of degeneracy mattering here was not so wrong, actually.
Yeah. Not wrong, but you cannot tell that from that picture. I mean.
Okay.
And Okay, so basically our requirement for the Hamiltonian can be roughly divided into two parts. The first is about its eigenvalue. So the only requirement for the eigenvalue is no degeneracy, and the requirements for the eigenstate is that it cannot be like block diagonal. It cannot be a block diagonal matrix. The Hamiltonian cannot be a block diagonal matrix in the measurement basis, or I can say in the computational basis. So this is can be intuitively understood using this picture. So basically, like I showed you before, the Hamiltonian, the direction of Hamiltonian cannot be parallel to the z direction. So basically, z direction is a measurement basis. So this requirements can be intuitively explained you by that picture. Okay. Is there any other questions? Okay. I'm happy to say that this is might be interesting for you. Okay. I'm also happy to say that maybe we can find some other applications of the random diagonal unitary in quantum information. Yeah, because there is not so much. And what is more, okay, from now I want to introduce some details to you. And the first detail is about the sample complexity performance. So basically, we found that if you can choose some good Hamiltonians, the sample complexity of our Hamiltonian shadow protocol is actually very similar with the original classical shadow using the random global Clifford. So for example, in this picture, we perform some like numerical and theoretical analysis for this problem, and you can see in the first figure here, the x-axis stands for parameter theta that determines the Hamiltonian. So when the theta is very large, in this case, the Hamiltonian we use is just some random Hermitian matrix. And you can see that in this case, the variance or the sample complexity of the Hamiltonian shadow will approach the original global shadow protocol. And what we know about the global shadow protocol is that it performs very good when estimating some low rank observables like the fidelity. So basically, if you estimate using the global shadow, using the random Clifford shadow to estimate the fidelity, the variance is upper bounded by some constant. And we also proved that we also theoretically and numerically show that our protocol, the Hamiltonian shadow protocol, also the variance of it is, or the sum complexity of it is also upper bounded by some constant if you estimate the fidelity or some other low rank observables. So this is another good thing for our protocol. Okay, if there's no other questions, we also perform some numerical tests, numerical experiment to show the. Okay, are there any questions?
Yeah, sorry. Like classical shadows are especially interesting if you look at things like k-local observables and stuff like this, and they have very, very nice properties for this. Is this retained in your construction?
Yeah. Very, very good. Thank you. We know that if you use like a global Clifford classical shadow, it is very good to estimate like low rank observable. But if you use like a random poly classical shadow, it is very good to estimate some local observables. And actually, our Hamiltonian shadow protocol also have local version. So basically, we found that you can use a completely non-interacting Hamiltonian to perform the Hamiltonian shadow. And we found that if you use a non-interacting Hamiltonian, our protocol is very similar with the local classical shadow, original local classical shadow, and it also performs very good when estimating some local like k-local observables.
So this is like the on-site Pauli variant of the classical shadow picture.
Yeah.
Very good.
Very similar. Okay, is there any other questions?
Sorry, can you just repeat what was for which Hamiltonians was it good for local observers, and for what Hamiltonians was it good for? Okay, non-interacting Hamiltonians is good for local observables, because non-interacting Hamiltonian, the evolution unitary of it is just a tensor product of some local Hamiltonian evolution unitary. And if the Hamiltonian is a very global Hamiltonian, it's very global and interacting Hamiltonian, then it is very good for estimating some low rank observable, just like the original global shadow using some global random global Clifford gate. Yeah, thank you. Okay. Thank you. Is there any other questions?
Can I ask about the robustness of the method to like nearly degenerate Hamiltonians? How close can the eigenvalues get before the protocol doesn't work?
Yeah. This is the reason why the evolution time should be exponential with the system size. So like I told you before, we hope the lambda t, whose elements is determined by the eigenenergy of the Hamiltonian and evolution time t, to be at least a random diagonal unitary 2D then. But if it is random diagonal evolution 2D then, or maybe as an extreme case, it is like the random diagonal unitary Haar measure. In this case, all the faces of different elements of different diagonal elements of lambda t should be independently sampled from 0 to 2 pi. So if you said the Hamiltonian is very close to a degenerate Hamiltonian, then you need a very large evolution time to split two different phases. So this is the reason why. So basically, if the Hamiltonian is very close to a degenerate Hamiltonian, you can always increase the evolution time t to avoid the bias caused by this thing. But at the same time, you need to increase. But at the same time, the evolution time might be exponential with the system size.
Yeah, that makes sense. Thank you.
Thank you. Any other questions? Okay, I'm happy to see there are so many questions. And actually, we also performed some numerical results and numerical tests that, for example, but this is not very important, I think. So basically, we use some, we set the Hamiltonian of our Hamiltonian shadow protocol to be like the Rydberg atom Hamiltonian, and use it to estimate some properties like the fidelity or the non-identical polystrings and the purities of the Rydberg atom systems. We choose these properties because these properties are conventionally hard to estimate using some conventional means, but our protocol performs well in this in estimating these properties. But this is not an experiment thing; it's just a numerical thing. And the final thing I want to emphasize here is that yes, our protocol has a disadvantage of the evolution time and the classical post-processing things, which makes our protocol cannot be scalable, cannot be applied to analog quantum simulators with like 100 qubits. But what I want to emphasize is that if for example you have an analog, let's imagine the case where you have analog quantum simulators with 100 or with 1,000 qubits, and after some analog quantum simulation, analog quantum evolutions, you want to estimate the properties of a subsystem containing like 10 qubits. In this case, and your ability is only to performing some Hamiltonian evolution with some fixed Hamiltonian. You cannot change the Hamiltonian form. In this case, I think our protocol is the most practical protocol you can choose until now. Okay, so I think although our protocol has some limitations, I think it is still meaningful for analog quantum simulations. Okay, if there's no other questions, I want to summarize. Hello. I want to summarize our the first work I introduced to you with some take-home messages. The first thing is the most important thing is that I think this is the most intriguing conclusion of our work, is that we prove a single Hamiltonian can completely learn a state. Basically, a single Hamiltonian evolution plus the computational basis measurement is tomography complete. This is I think this is quite surprising for me when I derive this result. And at the same time, the requirements of the Hamiltonian are minimal. So basically, if a Hamiltonian is not degenerate and it's not block diagonal in the computational basis, it can be applied in our protocol. And basically, if you can randomly select a Hermitian matrix, with a very high probability, it can be applied. It can be applied in our protocol. And at the same time, the performance of our protocol is comparable or is very similar with the original protocol, which used many independent random unitaries. Okay, so these are all the take-home messages of this work. Do you have any questions?
Just so maybe with the remark, this is beautiful. I mean, this is like great work, and it's also very much along the lines of like trying to lessen the burden of complicated protocols on the quantum side and make this readout easier. I mean, this is like actually interestingly, I will give a talk later today for the Munich Quantum Valley, and this will be also my take-home message then in a slightly different reading, but people are very interested in things.
Okay, thank you.
So this fact that you can use one Hamiltonian to learn any state. So I mean, obviously, if you evolve on the Hamiltonian.
Sorry. Your voice is very low. Can you raise the voice?
Yeah, maybe.
I can raise the voice of mine. Can say it again?
Yes.
Is it better now?
Yeah. Can say it again?
Yeah, so I mean, if I evolve on this Hamiltonian, there are like a lot of different states that commute with the Hamiltonian that I would not be able to tell apart just like from the Hamiltonian evolution alone. So the fact that this works is because you can always use the computational basis then to distinguish these states. Is this one way to understand this?
Your question is very good. Yeah, so this is another thing that is a kind of surprising. So basically, our protocol does not have no the validation of our protocol has no requirements on the state. Even if the state is commutes with the Hamiltonian, our protocol can also tomography completely learn this state. The reason is that we know this Hamiltonian. And if the state commute with this Hamiltonian, you can imagine this geometrically imagine this as the vector of this state is parallel to this Hamiltonian. And in this case, you will find that the state will not evolve under this Hamiltonian. So if you perform some measurements, perform computational basis measurements at different times, you will find that the memory result is all the same. Because the state is commutes with the Hamiltonian. So in this case, you know. And after finding that okay, the memory result does not change with time, you know that the state commutes with the Hamiltonian, and because the Hamiltonian is known, so now we still know what is the matrix form of this state rho. So the conclusion is that the validation of our protocol does not have no requirements on the target state rho. All the requirements is about the Hamiltonian.
Okay, thanks.
Okay, thank you. Is there any other questions about this work?
We had very many, so yeah.
Okay. If no, I found that I also have some time, so maybe I can briefly introduce some ongoing projects to you. And this project is all these projects are about the quantum learning, and I want you to know some of my research style, and please don't tell others. But I'm quite open for this thing. So if you have some related ideas you want to discuss with me, you want to join this work, you can send email to me and we can discuss. Okay. The first thing, actually, the first thing I want to share with you, I finished it like couples of days ago before the submission deadline of QIP. Is about the quantum fundamental cost of quantum learning. So basically, we know that if you have a mixed quantum state, and if you want to estimate some nonlinear properties of it, it is very difficult. For example, if you want to estimate the purity of the mixed state, or you want to estimate the virtual cooling information, so basically it is you want to estimate the value of trace O rho A square. And you want to maybe you want to estimate some principal component information of this state, which is like trace O phi A0. Here the phi A0 is the principal component of rho A. So basically, it is the eigenstate of rho A with the largest eigenvalue, and maybe you also want to estimate the Fisher information of rho A. And we know that estimating these properties are very expensive. What do I mean by expensive is that if you are restricted to single copy measurement, then estimating these properties accurately requires exponential sample complexity. But if you want to use like quantum memory to estimate these properties, you need to at least double the system size. For example, you need to double the system size to perform a swap test to estimate the purity of the state. So,
this relates, of course, to also a huge literature. I mean, also here again in the call, there's many experts on the power of quantum memories and so on. I mean, there's a lot now that's emerging on the power of having access to larger like numbers of copies, aka a quantum memory, and also to obstructions when you don't have this. Like, for example, for purity, it's known that if you have 2 copies, you can easily do it.
Yes.
Efficiently, whereas if you have 1 copy, there's obstructions and so on. Yeah, do you relate to this, to these kind of?
Yes, of course.
Good.
Yes, maybe some of you are familiar with these papers, like the exponential separation between learning with and without quantum memory. So I'm talking about that thing. So okay, so we know that those papers. So basically, recently there's many papers concerning about the fundamental limitations of quantum learning. But we know that if you want to estimate this, those papers told us that if you want to estimate this property, you need to either double the system size or you need to pay exponential sample cost. So a very natural question is that can we explore other resources in addition to sample complexity and quantum memory? Can we explore other resources that can help us to achieve the constant sample complexity in estimating these properties, while at the same time only increasing this system by a constant number of qubits? So this is very important and natural to ask these questions. So in this paper, we prove that we can do this. What kind of resources we use is the purification. What is the purification? So let's assume that the rho A, the target mixed state is a low rank unknown low rank mixed state, which can be purified by a global pure state with a constant number of additional qubits. What do I mean by purification? Is that we can now perform quantum operations and measurements simultaneously on the state rho A and rho B. And here rho and rho B together is a global pure state. And at the same time, the rho B only contains a constant number of qubits. For example, maybe only contains a single qubits. We proved that in this case, with only single copy measurements and operations on this rho A and rho B, we can estimate these properties, these 4 properties, nonlinear properties, with a constant sample complexity. And at the same time, because rho B is only contains a constant qubit, so we only need to enlarge our system by a constant number of qubits. So this is our.
Sorry, again, just to see if I got it right. Your assumption is that the state is low entangled, not that the low has a low rank decomposition. This is what you mean, that that the state that you want to purify is the purity is already large enough, or that the entanglement is low. Is this assumption?
Yeah.
Okay.
Yes. My assumption is that the purity is large and the rank of rho A is a constant. So there exists a constant.
And the purification is low entangled. Yeah.
Yes. This is my assumption. Yeah. So in this assumption, under this assumption, I found that these properties can be accurately estimated with a constant sample complexity by adding a constant qubit in my processor. Yeah. And what is more important is that we also proved that if you don't have the quantum physical access to this purification system, but at the same time you know your system, you know the state, the rho A, the target mixed state is a low rank and it can be purified by a constant number of qubits, but you only know that it can be purified by them, and you know the rank of it, but you don't have the access to this rho B. Then estimating these properties is also exponentially hard. So this is our second conclusion. So basically, we prove the exponential separation between quantum learning with and without purification. Okay. We also explore some generalizations of our protocol from the state learning to channel learning. Like we found that maybe learning the unitarity of a channel also has such kind of separation, exponential separation. And so basically this conclusion is a conclusion about sample complexity, or is about the computation. So we explore some applications of our conclusion in quantum cryptography. I think they are quite interesting. Is there any questions? Okay, if no, I continue. Another thing I'm recently very interested in is based on is about a very general framework called I call it the environment learning. So basically this framework is kind of like imagine now I want to estimate the property of an uncontrollable system. There's an uncontrollable system, and I want to estimate the properties of it. But what I have is that I have a controllable system. Is a controllable system, and the controllable system is interaction with the uncontrollable system with some interaction, and maybe we don't know that we don't have the knowledge of this interaction, and so my question, the thing I'm recently thinking about is how to use this controllable system to extract information of this uncontrollable system, and in the case that we don't know the interaction knowledge, we don't have the interaction knowledge between these two systems. And I mainly have two directions, research directions. The first is environmental learning. So basically we treat the uncontrollable system as the environment of our environment, and the controllable system as our quantum device. And we at the same time we can perform arbitrary operations and measurement on our quantum device. And we want to use these operations and measurements to extract the information of the environment. And so my question is that what kind of information of the environment can be extracted using this in this scenario? But at the same time, I want to assume that we don't know what is the interaction, what is the interaction form. And the second thing is I think is not very natural. So second direction is that I treat the controllable system as our computational space, and I treat the uncontrollable system as our leakage space. And the interaction between the controllable system and the uncontrollable system is a leakage error. But I don't know the form of this leakage error. So recently I'm thinking about if we can control the computational space, what kind of information of the leakage space can be extracted. Okay, if there are no other questions, I will continue. The final thing is very related with your recent work. I added here because I remember that you recently, I think it's Daniel Miller's work. I don't know if he's here. You recently have an entanglement detection paper based on the purity criterion and the Bell-state measurement. So basically, you estimate the purities of bipartite states and its reduced data matrix, and then compare their purities to decide whether the state is entangled or not. And I recently also have an entanglement detection work that is very similar with your work, which is also based on the Bell-state measurements. So, but my work is based on the PPT criterion. So I'm not sure if you are familiar with the PPT criterion. Basically, it's positive partial transposition criterion. So basically, the positive partial transposition criterion is constructed by deciding whether the state after the partial transposition is a semi-positive matrix or not. And mathematically, it is equivalent with finding a pure state, and then using this pure state to construct unobservable by the partial transposition, and then measure this observable on the target state rho. So if you can find a pure state phi to make this expectation value be a negative, then we know that rho is an entangled state. So this is the PPT criterion, and so it might be easy to develop some protocols to verify the PPT criterion, because you can search over all the phi state, which maybe you can search over all the phi which can be prepared by some like variational shallow circuits, and then to find if there exists some negative values. But actually there are some difficulties. For example, if phi itself is a very it can be prepared by some shallow circuit. In this case, even if phi can be prepared by some shallow circuit, but after this partial transposition operation, this might be a very complicated observable to estimate. So basically, maybe you need a very deep quantum circuit to estimate this observable. And our work is based on a very simple observation. The observation is that if you want to estimate this function, so basically trace the rho sigma partial transposition, we found that this is actually equivalent, but this is actually very simple. This is equivalent with performing some joint operation on the joint state of rho tensor sigma. And here, this is so phi A plus is just one Bell state, and this is swap operator. So what we found is that all these observables can be measured using Bell state measurement. And now with this equation, now the phi TA, this thing, the phi now turns from a mathematical object to a real quantum state. So we can develop some protocols to verify the PVD criterion. So basically, here rho is the target state, and then here you can use some shallow variational circuit to prepare the reference state, and then interfere it with the target state using the Bell state measurement. And then but here different Bell state measurement has different post-processing strategies because they need to be applied to estimate observables of different observables like phi A plus and SB. Then we can search over all the variational states to search if there is a negative value to decide whether the state rho is entangled or not. And we perform some numerical tests. We found that even if the depth of this the depth to prepare this reference state is very shallow. For example, if it only has one depth or two depths, our criterion is already much better than the purity criterion, some entanglement criterion. Okay. So this is all of my talk. If you have any questions, I'm very happy to answer them.
With respect to learning the properties of the environment, what kind of properties would you be interested in? What are the things that you would like to learn?
Yeah, I'm happy to share this with you. So for the environmental learning, I'm now you know that there exists some protocols, some works that use the interaction to estimate the dimension of the environment. So now I'm thinking about, can we like learn some more detailed information? The detailed information is about memory effect for this environment. So I'm recently thinking about how to learn the memory effect of this environment, like how many freedom is in the memory is in the memory of the environment, and the leakage.
So like a Markov order or something like that.
Yeah, similar, very similar. And for the leakage thing, I'm recently thinking about how to estimate the dimension of this leakage space. So basically, I want to ask maybe how many freedoms is coupled to our computational space.
Yeah, that's it. I have a follow-up question on this. Like, I mean, can one think like of model selection ideas in the sense that there will be, well, obviously loads of degrees of freedom of the environment that are there somehow, but only very few will matter significantly. There's a kind of a relevant subspace somehow, and then there's a complement that's not really taking part in any of this. So can one kind of like learn the effective dimension or so of the environment, or something maybe more like continuous, like some like maybe an isotropic quantity or something that captures like how many degrees of freedom of the environment matter? Is that something that makes sense?
Yeah. But I think this is already there already exists many works about this problem. So yeah, so what I want to do is trying to extract some more detailed knowledge instead of just the environmental dimension.
Very interesting. Thanks.
Thanks. Is there any other questions?
Yeah, maybe I can have a final question about the last part about the entanglement detection with this PVD criterion. So you compare this with the purity criterion, but have you compared with this so-called P3 PPT? I don't know if it tells you something. It's related to the moments of the partial transpose. So it tells you something that the trace of rho partial transpose raised to 3 compared to the purity, things like that. How does this perform? I think it would be equivalent as if in your in your picture, this U theta, this variational circuit prepares something like rho partial transpose itself. So you would be computing something like that. You can also construct entanglement criterions based on the moments of the partial transpose. Have you compared with something like that, or maybe specific? Okay, and how does it perform when you compare with that and not just with the purity criterion?
Yeah, I'm very happy to say that there's someone knowing the P3 purity criterion, because I'm also working on it. So the reason that I didn't compare with the P3 purity criterion is that and the reason that we choose the purity and fidelity is that so basically you can see that our protocol can only requires to enlarge the system twice. So basically, if rho is n qubit, our protocol only requires a quantum processor with 2 times n qubits. But if you want to estimate like the P3 PPT criteria, P3 PPT, you need to enlarge the system like twice, like to the 3 times of the original size.
Well,
so,
you can also do it with shadows. Actually, we did it with shadows. This P3 PPT experimental demonstration.
Yeah, of course.
Okay.
Of course, but then you need exponential sample cost.
Yes, that's true. Yeah, with sensor size.
Yeah, I see Daniel Miller posted some things. Thank you.
Okay.
Okay. So also thank you for your question.
Fair enough.
But so in this PPT criterion, like you have to find a psi such that is sort of the task of the algorithm also, right?
Yeah. So we propose that you can search over like a shallow variation of circuits.
And then how far, like, I mean, you anyways have to store like two states of size log k roughly.
Consider again.
I mean, you will have to store the reduced state, and you have to also you also require the other register for like the psi state, right?
Yeah. Yes.
So if you require that much quantum memory anyways, wouldn't it be cheaper to directly do some Pauli sampling or something from 2 copies of the reduced density matrix?
Yes, but our target is to perform like quantum entanglement detection. So this is the reason we compare our protocol with purity estimation, because if we have twice the system size, then it is very easy to estimate the purity and use the purity to detect entanglement. So I guess what you mean is that maybe we can also perform some Pauli observable estimation using protocols like the shadow, something like that. And but the question is that how can we design the entanglement detection protocols?
You don't only want the number of what is the purity, but you also want what is the witness for the purity.
Yes, of course. We know how to construct the entanglement witness based on purity, but we don't know how to design the thing based on the Pauli samples. But if you can design something based on Pauli samples, we can also compare our protocol with that protocol.
Yeah, I see. Yeah.
I also have a question about this figure, because in my experience, it matters a lot when you compare PPT against purity. It matters a lot which subsystems you look at. So for PPT, equal bipartition is usually good, and for purity, like one subsystem versus many subsystems performs better. So can you explain this plot again a bit better? What is, for example, green against red? So K is the size of the subsystem, or?
No. Yeah, this is quite detailed, I think. So basically K is the y-axis stands for the ratio. So basically we randomly select a state rho, and then we use many different kind of entanglement criterion to test whether rho is entangled or not.
And how big is rho?
What?
How many qubits?
this finger is 6 qubits. 6
Okay.
qubits.
And what is K?
Yeah, 6 qubits. K is the parameter determines the probability distributions used to sample row.
Okay,
so basically,
but how do you define the purity criterion then and the PPT? Like what bipartition do you look at?
Okay. So basically, if K is large, then this means that the row is very close to the maximally mixed state. So the state is very unlikely to be an entangled state.
Yeah.
And the purity is okay. So basically, I fix the partition of row. So
how do you fix
it? Row A and row B has 3 qubits, and I fix the partition.
Yeah, but then it's not surprising that the purity criterion is so bad.
Okay.
I think it would be better. Yeah, maybe this is a bit not fair for the purity criterion, because the purity criterion would perform better if you would compare 5 qubits against 1. I would expect. So yeah.
Yeah, of course. But what is good for our protocol is that you see this like this blue line. This blue line, I use a single layer. I use a single layer variational circuit to prepare the reference state, and use it to detect the state of row by the PPT criterion. And we found that a single layer is also already performs very good.
Yeah. Yes. No. I think it's a cool technique. I just say the purity criterion is better than it looks in this figure. I would expect, but yeah, that's what I have to say.
Okay. Thank you for your comments. Actually, we have discussed this maybe 1 year ago, and I'm very slow in this work.
Yes.
Okay, thank you for your comments.
Can I ask another question on the first part again, on the simple Hamiltonian shadow? I mean, as you know, there's many ideas of Hamiltonian learning, which is of course a different task, where you learn the Hamiltonian, not the state. Well,
yeah,
that's for granted. But you surely also know that in that setting, like mid-circuit measurements help a lot. There's all the highest level. There's kind of 3 types of schemes, like short time evolution schemes that make use of qubitization, trotter, you name it, and then they get good sample complexity bounds. Then the deep circuit things via tensor networks and maybe free models, and then there's the mid-circuit measurement type of Hamiltonian learning schemes.
Yes.
Would it help to do mid-circuit measurements here, or is that a pointless question? Because I've not seen this in this context. It should help in the same way, no?
I think your question is all very interesting, but it's beyond of my original.
Fair enough.
But actually, because I think because our target is to develop something for analog quantum simulators, so I think most of the analog quantum simulators have no power of performing, and do not have the ability to perform the mid-circuit measurement. I think. If you have the ability to perform the mid-circuit measurement, maybe I don't need to use such kind of thing to perform tomorrow work, because maybe your circuit is already powerful enough to perform some like universal gate set. Hey, hello, Yes, you are.
No, that's interesting. Thanks a lot. Great talk. Also, I mean, I really enjoyed it.
Okay, thank you. Is there any other questions?
Good. I think we had loads of questions along the way. Then thank you very much indeed again for this wonderful talk, and also thank you everyone for coming in and asking these many questions. It was a great discussion, I thought. We catch up very soon, Zhenhuan.
Okay.
A message. Thanks so much indeed. That was really fun. That was great.
Thank you for your patience. Thank you for your questions. See you later.
Yeah, thank you. Goodbye.
Bye-bye.
See you.